So moving right along from our textbook to the next section, the topic is work done. We're going to take a look at work done in two different contexts today. The first one is very, very simple, work done by a constant force. You could see that in a non-calculus class. But the part that we're going to spend the most of our time today is work done with a variable force. That's where you're going to need to know about integration, and that's where the problems become more challenging and interesting. So first of all, what is work done in physics? And by the way, how many of you are taking Physics 1 this semester? I see several students taking Physics 1. You probably are going to discuss work done in that class as well. In general, work done is basically the energy required to do a certain job. And the units we're going to use in this class is mostly going to be foot-pounds. But in different in different systems, you might use Newton meters or joules, or even like watts, kilowatt hours, watts, or something like the different measure units to represent the energy that is required to accomplish a task. So we're going to start with a very simple example. And like I mentioned, this example comes from your textbook. So if you like, just open to that page and follow it from there. So we want to determine the work done in lifting a 50-pound object a distance of 4 feet. And the simple definition of work is, again, you may want to jot this one down at least for today, that work equals force times distance. Force multiplied by distance. But the thing is, the force should be applied in the direction of motion. Like in physics, you see more complicated formulas like F times D times cosine theta, perhaps, because then you take the force in the direction of the object that is being pushed. So in this case, we're just looking at a very simple formula. Work equals force times distance. And in that formula, the assumption is that the force is applied in the direction of motion. Like in this example right here, a very basic example. We have a 50-pound object. We're going to lift it directly up, and the force is being applied directly perpendicular in that same direction of the motion. So work done would be very simply applying this formula. Work would be force times distance, and the force will be equal to the weight of the object that you're trying to lift to be able to lift that object. So force will be equal to the weight, which is 50 pounds in this case. And how many feet are we lifting it? In this case, 4 feet. So in this example, the answer is 200 pounds. So as you can see, if the force is in the direction of the motion, and you're applying a constant force throughout the entire region, then work done is a very simple formula, a simple product, the product of the force applied times the distance during which you've applied this force. But again, the interesting cases are when you don't have a constant force. For instance, think about sending a satellite into space. As this satellite gets away from the Earth, do you need to apply more and more force or less and less force, do you think? As you're getting away from the Earth's gravitational pull is decreasing, right, as you go further and further away from the Earth. So in the beginning, you have to apply a very huge, large amount of force, right? But as the satellite gets away, further and further away from the Earth, the force that you have to apply decreases. You have to apply less and less force to be able to push it in the same direction. So, but it's basically a different amount of force in every distance to be able to push it away from the surface of the Earth. So that would be an example of a variable force. So again, the typical examples we're going to look at today apply when you have a variable force. And let me just try to show you the theory a little bit to you here. Again, this is from the textbook, so if you like, just glance at this. Don't try to write it. Let's just try to understand it. If you need a note, see me after class, or just take a look at your textbook. Okay. So if finding work done is so simple when the force is a constant, we try to use this idea when the force is variable. So say you have an interval from A to B, which we partition as x sub 0, x sub 1, all the way to x sub n. If the force is variable during this time frame, this distance, what we can do is just like we've done all the way in the past, which is, slice the problem, dice it into an easier question, and then solve the easier problem, then generalize it. So if you have a variable force over that length of distance, what you can do is you can look at the force in a small amount distance where it's actually fixed. So even though it may be, for example, say your force is something like this, it's variable, right? But if you look at a small amount distance, say from here to here, in that little distance, it might actually look like it's a fixed force. So within that little time frame or distance frame, you can apply work equals force times distance formula. And then from there, so we first partition it, our length of interval from A to B. And then within each interval, we use a simple formula. To find the work done in that interval, just take the force in that interval times delta x, or the distance of the x, so between the distance between this point and that point. And what will be the total force, rather total work done? It's the summation of the incremental work done. And this is an approximation. What will be work done in the exact format? You would have to take a limit as n goes to infinity of the incremental work. And the incremental work is, basically, I'm just copying this from the line above. And as always, what do we replace limit of a sum with? Anytime you're trying to sum something over a large number of intervals, and as n goes to infinity, you're going to have infinitely many intervals. How do we simplify this limit of a sum? What we've done in the past to simplify that. Just integral, right? So that means total work done for a variable force equals the integral of, and basically all we have here is the function f of c sub I and delta x, so that will show up as f of x dx. So compare this with the formula we had a few moments ago. Work equals force times distance, right? This was for a variable force, right? Rather, I'm sorry, this one was for a constant force. Work equals force times distance. So for a variable force, see how similar the formula is? But instead of a strict multiplication, you have the integral of force times distance, integral of f of x dx, because now you're looking at force over small increments, and you're adding those increments over the given interval from A to B. So basically, that is our formula. Work done equals the integral of force applied times dx. Okay, we're going to do some examples. Let's see. I'm going to come back to that one later today, I think. I want to start with this one today. There are many types of examples in this section. There is the spring mass problems. There is the propelling an object into space. There is these kinds of questions, which is filling in or emptying a container with some liquid, such as water or gasoline or something like that. Today, I'm going to emphasize the last type of problem, which is filling in and emptying the container with a given liquid. And next class, if time permits, I want to go back and do a few other kinds of examples as well. If you look at your group activity, I mainly have this kind of problem in there, which is the type of work done questions where you're dealing with a container and you're pumping something in or pumping something out of the container. So the amount of energy required to do that job, that's the type of problems that we have at the moment at our group activity also. Okay, so starting with this question, find the work done to fill the cylindrical container. And for these questions, we're going to use the weight of water to be 62.4 pounds per cubic feet. So suppose we're going to fill this container from a hole that is at the bottom of the container. What would be the work done to accomplish this task? For all of these questions, I will begin by selecting not a representative rectangle like we've been doing in the last few sections, but I'm going to select a representative slab, a thin slice of the given container. Okay. So we know that work done by a constant force equals W equals force times distance. What I'm going to do first is I'm going to find what I consider to be delta W, which is a small amount of work that is work done for this one slab. How much work is done to put that slab from the bottom point? Think of it, there is a hose on the bottom that we're pumping liquid from the bottom of this container. So my first question to you is, how much work has been done to put that slab into position from a point at the bottom? So remember, work equals force times distance. I'm going to call this delta F, a small amount of force, times distance. Okay, the force required to lift that slab must equal to its weight, the weight of the slab, times the distance it was carried. Okay, as for the weight of the slab, since we know that the weight of water, or the density of water is 62.4 pounds per cubic feet, how could I determine the weight of that entire slab? 62.4 pounds per cubic feet. Again, the distance will be outside over here. What should I be multiplying this by to get the weight? This is the density, right? To get the weight of that slab. And if you look at your units. Here you have pounds per cubic feet. What kind of a unit would you need to multiply that by so you end up with pounds for the weight of that slab? You need to multiply by what kind of units? Cubic feet, right? Cubic feet times pound per cubic feet, you're going to end up with pounds. So in other words, cubic feet is units for volume, right? So what is the volume of that thin slab? That's what we need to determine. What is the volume of the thin slab? Okay, well, it's a thin disk. The radius is given to be 5. At the moment, let me just say volume of the slab, and then I can fill that in the next step. Volume of the slab. So this first part gives me the weight of the slab, and remember, and that's the force required to lift it. And force times distance is work done. So we're in the right direction. We have force times distance, at least for a single slab. What I need right now is the volume of the slab as an equation. What is the volume of the slab? Here we have 62.4 times what? What is the volume of that slab? Any suggestions? What is the volume of a thin cylindrical disk? Pi r squared times what? Times the thickness, right? What is the thickness of that, do you think? Delta y, right? Because you are going from a distance along the y direction to another distance in the y direction. So something like this will always have a thickness of y because you are incrementing along the y direction, right? So that thickness is delta y. So the volume of slab equals pi times radius squared. Radius was 5 times the thickness of the slab, delta y. Okay? And how about that distance that that slab was carried? How can I represent that distance? How much was it carried from there to there? Well, it depends on how high it went, right? Each slab will go to a different height. That's why you need variable force here, because each one is placed into a different level. So for each one, you're applying a different force, basically, right? Or actually, each one is going to a different distance in this case. For this particular case, each one has the same exact weight and exact force applied to it. But what is the distance? Each one is different, so it will have to be a variable. What variable should I use to represent this distance right here? You're going from here to here. What is that distance usually represented by? Y. So that's why we're going to have a y here. So the distance that slab was carried is y units. It's a variable because it depends on how high it goes. That's why it's a variable. So now we have something very important. We have delta W, which is the work required to lift that one single slab, is this amount. How will we find the total work done? You're going to integrate your delta W to find the total work done. So integrate 62.4 times pi times 25 times, you know that dy, I'm going to put it all the way at the end. And what am I missing in here? What's the only thing that I didn't carry from this step down to the next step? My delta y became dy. Why? Y was the only thing that was missing there, and now I have it. And how about the limits of integration? Since I have a dy, guess where the limits are going to go from where to where? It'll go from 0 to, look at the y limits, right, from 0 to 20. And notice how easy this integral is to integrate. Just take out all the constants. And integral of y is y squared over 2. Now go from 0 to 20. And let me give you a moment to get the answer, please. And what do we get? It's going to be a large number. These questions with the foot-pounds unit numbers tend to be usually pretty large. Did we get any values? I'll go ahead and multiply with pi also. $980,177 roughly. And the units will actually always be foot-pounds. The reasons, remember, work is force times distance. Force units will be in pounds, and distance will be in feet. So usually we're going to leave the answers in foot-pounds. But remember, with different units, like different systems, like it might be Newton meters or things like that. But our examples mostly are going to be in terms of foot-pounds. Okay, how about the next question, part B? Find the work done to pump out the contents of the container, assuming it's full of water, this time to the top level of the container. In other words, instead of filling it in, we're emptying it out. So we have the same exact figure to begin with. But instead of filling it in, we're going to empty it out. In other words, again, think of this cylinder as a union of a bunch of thin slabs. So the bottom slab will have to be carried to the very top level. The next slab will have to be carried to the top level. So each and every one of the slabs will have to be carried to the top level. Any thoughts as to what the answer might be? Comparing it with part A. Part A, we were filling it in from a hole at the bottom. We put the slabs in position. In part B, we're emptying it out from a hole at the top. Any thoughts what the answer, how it might relate to the answer from part A? Filling it in versus emptying it out. Do you think some of you thought maybe it will be the same? Let's see. I think you are on the right track if you said it's the same. So take the same exact figure, but instead of, so work done equals, it's still force times distance. And force for each slab will still be the same, which is 62.4 times pi r squared. But instead of y, remember, y was the distance when you're filling them in. So when you were filling them in this slab to be put in place, it went this distance from here to here was y. Now we're emptying it out. If we're emptying it out, it has to go from where it is to the top level, And remember, the total height was 20. So how would you represent this height? Now we're pumping the contents out of the container. We're going from that, whatever level it is, to the top level. So what would you use for the distance it's carried? 20 minus y. So now instead of y, we're going to have 20 minus y. And how about the limits of integration? Basically, you have a slab anywhere from 0 level to the 20 level. So the slabs vary still from 0 to 20. So let's go ahead and do this as well. So take out all the constants. Just integrate 20 minus y from 0 to 20. And I'm going to call all this just a big constant c, so I don't have to keep writing it. And integrating this, you get 20y minus y squared over 2, going from 0 to 20. Now let me wait for a moment to see what number you're going to get for this one. So we want the constant times 400 minus 400 over 2, or 200. So basically, I want that whatever the constant was times 200. And did anybody get an answer for this? Same exact answer as before, which was 980,177 foot-pounds. So for this question, it didn't make a difference whether you were filling the container in from a hole at the bottom or you're emptying it out from a hole at the top. By the way, these questions are always going to be the same way. When you're filling it in, you're always going to fill it from a hole at the bottom, because that's what's causing energy to be given. You have to pump, you have to have maybe a motor to pump liquid into there. Because think about it, if you're emptying it from a hole at the bottom, do you really need any work done? Just open the container at the bottom, the gravity would do the work, right? If you were emptying it from a hole at the bottom. So usually the work that we need to provide is, if you're emptying it from a hole that is at the top, like you're pumping the contents higher up, that's causing the need for an energy. That requires energy. Or if you're filling them in, you're not going to fill it from a hole at the top, because if you put a hose there, the gravity would just do the job. It will fill it automatically. So when we're emptying something out, we're going to empty it from a hole at the top. When we're filling it in, we're always going to fill in from a hole that is at the bottom. Okay, now a different shaped container. Let's take a look at this one. Find the work done for a conical container. In part A, we're going to fill it in. What is the work done to fill this container with water? Again, remember, for every question in the first 3 sections, I had asked you to pick a representative rectangle. That was really important. Here, the same thing applies, but instead of a rectangle, I want you to pick a slab, a thin slice of the cross-section. I'll begin by doing that. Okay. Pick a slab, which is a thin slice of the cross-section. Okay. And what will be the thickness of this slab? It will be delta y, right? And every one of these slabs, we're going to always cut them perpendicular to the y-axis. They will always have a thickness of delta y. Okay, so I want to find the total force required, total work rather required to fill this container. So once again, work equals force times distance. First, I'm going to find the work for one slab, so I call it delta W, which is equal to a small amount of force to lift it times the distance it has been lifted. Once again, what is the force in terms of, again, it's water. You can assume 62.4 pounds per cubic feet. And the force required to lift that should be equal to the weight times density. Actually, let me put it this way. Weight, we still have the distance there. And the weight can be written as volume times density. And you still have the d, the distance. So again, to lift something up, you have to apply a force to it. That force must be equal to the weight of the object, and the weight of this thin slab equals the volume of the slab multiplied by the density of the slab. Okay, this is not as clear-cut as the last example. In the last example, when we got the volume of the slab, it was a constant radius of 5, right? No matter where you were in the container, the radius was 5 units. This one depends on how high you are as to what the radius of the container will be. So it's not a constant. What could I call this distance from here to here, the radius of the slab? What could I call that? It's not really going to be 5. Only the top slab is going to have a radius of 5. I already had a very good suggestion. I heard x. Would you agree with that? The radius of the slab is x? Because it depends on where you are, right? It's going to be a little bit wider as you go further up. So the radius of the slab is x. Okay. So now what is the volume of the slab? Who can help me out with that? The volume of the slab. This is just a cylindrical figure, so just area of the base times the thickness. Area of the base is pi r squared. And how about the thickness? By the way, since radius is x, I might as well put the x in there. So I'm going to put pi x squared. And how about the thickness of your slab? What is the thickness? Delta y. Density is always 62.4. And how about the distance? Since we're filling the container in, we're filling in a container from a hole at the bottom. So you're taking this slab from here to this position. How much distance did that slab have to be moved to be put in place? What is that distance from the x-axis to wherever the slab has been placed? Is it going to be a fixed distance of 10? Or depending on where the slab is? Exactly. James said it, y, because we were filling the container in. And in general, you're going to see that when you're filling something in, the distance is y. When you're emptying it out, it might be something like 20 minus y, or whatever the distance that it has to go further from that point up. So we're filling it in, that distance it has to go is y units. There is one problem here, and that is, you see the x squared in our equation? And the delta y in our equation? The delta y tells you that all the variables must be in terms of y. So this x squared is breaking the rule there. We've got to get rid of the x squared somehow. But here's what we can do. We can use a similar triangle ratio. We know this side is 5, this side is 10, this is x, and this is y. So give me a ratio where I have an equation, and I can use that to get rid of x and write x in terms of y. What kind of a ratio could I set up here? For example, the ratio of x over y is equal to 5 over 10. Good suggestion. The ratio of x over y is equal to ratio of 5 over 10. That means 5y over 10 equals to x. In other words, x equals y over 2. X equals y over 2. So take that information, now that you know x in terms of y, and put it back into our equation. So we're going to have, and by the way, I will factor all the constants up front. Pi times 62.4 times. Instead of x squared, I'm going to write, what was x once again? Y over 2. And I still have a y up there to be brought down, and I still have a delta y. Okay. So remember, this is the work done for one slab to be put into position. How do we find the total work done? So what should I be doing right now to find the total work done? This is work done for one slab. I want the total work done, so what should I be doing? Yes, Garrett? Integrate it, because integration will give you the sum of all the slabs being placed in position. The first one, the second one, the third one, infinitely many of those basically as the thickness gets close to 0. So integrate the above quantity to find the total work done. That was just for one slab. We want to do it for all the slabs. So integrate pi times 62.4 times. As I'm writing this down, I'm going to expand this a little bit. Y squared over 4 times y dy. And how about the limits of integration? They should come from the y-axis, right, because of the dy. So the limits of integration should be from where to where? From 0 to where? 10. So let's take all the constants outside and then integrate the remaining quantity. So I have a y cubed left on the inside. And integrating that, you get y to the 4 over 4. And plugging your limits from 0 to 10. And let's see what you guys are getting for this answer. Anybody who got something? That sounds right. 122,522. Could anybody else confirm this finding? I know Courtney's checking, so I'll wait. You got the same thing? Okay. In part B, we have a very similar question. But now instead of filling the container in with water, we're going to pump out the contents to the rim level. Basically, we're going to empty the container. So basically, we're going to empty out the container. By pumping the contents to the rim level. You can almost imagine that this being a tank of gasoline or water under the ground, and somebody wants to bring it up to the ground level, so they're pumping the contents to the rim level. In that case, the rim level will be the ground level. And the assumption is that the container is full of water. What is the only thing that's going to be different here? Let's think about it. You would still begin by picking a rectangle, a slab that is from your region. So you still have a cylindrical thin slab there selected. The weight that you have to move that slab has not changed. It's still full of water. It's still the same shape of container. So the weight, the force has not changed. But how about the distance? In the previous question, we're filling the container in. And again, we always assume when we're filling them in, we assume we're filling from a hole at the bottom. So in the previous question, you use this as your distance, right? Right now, we need to use this as our distance, because that slab has to go from where it is to the top level. It has to be pumped up to the rim level of the container. So the only difference is going to be the distance. What is the distance going to be for this question? I heard 10 minus y. Would everybody agree? Yes, when you're filling it in, the distance you're using was y units to put into place. When you're emptying it out, the distance, it has to be moved from that point to the rim is 10 minus y. So the only difference is distance should be 10 minus y. So let's use the same exact integral from the previous step. Same exact integral. I'm going to go way back to where we formed it over here. And I'm going to change y with 10 minus y. Change y with 10 minus y. Actually, let's go here. When we got rid of the x's and we had only y's remaining, let's go to that level. So the total work done to empty out this container by pumping the contents to the top level equals, and I know I'm going to have to integrate this quantity anyway, so pi times 62.4 y over 2 squared. In other words, y squared over 4 times y, excuse me, instead of y, what do I need? 10 minus y. That's the only difference. Yes, you certainly can, and I'm going to do that in my next step. You can take all the constants, including pi and 1/4 outside. What are the limits of integration in this case? Same as above, right? 0 to 10. Okay, so let's take all the constants outside and then integrate. 62.4 times pi over 4 times the integral of, I will distribute y squared times 10 minus y. And then let's integrate each term. So 10y cubed over 3 minus y to the 4 over 4. Once again, going from 0 to 10. Once again, please let me know what you're getting for this answer. And then we're going to do one last version of the same problem. Then you've seen all different varieties of this kind of problem. So hopefully you can do all sorts of questions that use these same varieties. Like sometimes they fill the container halfway. Sometimes they fill it in. Sometimes they empty it out. Again, this example covers a lot of different grounds here. Okay, anybody with an answer for this question? 40,841. Okay, could somebody else confirm it? And Courtney can confirm. Okay, and units once again are foot-pounds. Why did it turn out that emptying out requires so much less work than filling it in? Let's think about that for a moment. The last problem, it was cylinder. It was the same width throughout the region. It was same work required to fill it in as it was to empty it out. Here, emptying out was a lot less work. Can anyone give a rationale as to why that happened? It's thinner at the bottom. Think of the slab that is at the bottom. That's the smallest slab, right? When you're emptying it out, the smallest slab had to go the farthest distance, right? When you're emptying it out, that smallest slab, you had to carry it all the way to the top, right? When you were filling it in, on the other hand, you had to put into position the biggest slab, the longest distance, right? When you're filling it in, that biggest slab that was all the way on the top, that had to be carried the longest distance, which was 10 feet. It had to be carried that far. When you're emptying it out, the smallest one, which is the one right here, is being carried the longest distance. So that's why when you're emptying it out, you require less work, basically, because you have smaller slabs that had to be carried such a long distance, the bigger slabs that had to be carried only a smaller distance when you're emptying it out. Yes? Right. We always assume when we're filling it in that we go from the bottom up, that we're pumping a liquid into the container. Right. Because otherwise the gravity does the job. If you just open the container, if you have a hose on the top, the gravity would fill the container and there would be no need for any work, right? So say you have a tank of gasoline under the ground. When we're emptying it out, we're basically emptying out to the ground level. You're lifting it up. That process causes energy to be used. Okay, here's a little variation of the problem. These we're not going to evaluate. I just want you to set them up so you see these variations a little bit. Let me try to push everything a little bit further down. All right. Part C. Find the work done to pump out the water to the rim level, but this time assume the container is full only up to an 8-foot level. So once again, we're going to pump out the contents to the top, but the container is only full up to the 8-foot level. Once again, I'm going to pick a slab from the region. If you're pumping out the contents to the rim level, what will be the distance that this slab has to be carried? From where it's standing, for any given slab, from where it is, since you're pumping out the contents to the top of the container, what is the distance that it has to be moved? Which is this distance, right? You're emptying out the contents. You're pumping the contents to the top level, to the rim level. So what distance will it have to be carried? This is the distance I'm looking for. From where it is to the rim, how far will it have to go? Is that y? Or is it 10 minus y? Y would have been this distance, right? From here to here, that would have been y. If you were filling it in, but now you're emptying it out, so it should be 10 minus y. Minus y. Okay. Has the weight of the slab changed? It's still full of water, still 62.4, still pi r squared times delta y. The weight hasn't changed. It's going 10 minus y. So this is so much similar like the last question. So what's the only thing that's different than in our integration process, in our final answer? What is the only thing I should change from that? So we're still pumping it to the 10 minus y level, right? The weight is still the same. I heard a good suggestion from Courtney, which was integrated from 0 to 8. Would you agree? Because now the water is only full to the level of 8 feet within the container. So those slabs, you have to worry about, you have to set them up each one from 0 to the 8 level. So that's exactly what we're going to take it from the previous step from over here. And the only thing we have to change is go from 0 to 8. So work done equals, pull all those constants outside. I might as well, but you can write it in either format, 62.4 times pi over 4. Okay, what else do I need? An integral sign from 0 to 8, because it was only full up to that amount. And then inside we had y squared over 4, and then we had 10 minus y. Let me ask you a question. Why do we not have here 8 minus y? Why do we have 10 minus y? Why didn't this change also? Can anybody explain that? Right, Gracie? Because that's the distance we're trying to carry it to. We're not trying to carry it to a level of 8 foot. We're trying to carry it to a level of 10 foot from the ground level, from the bottom of the container. And the distance it has to move at each slab is 10 minus y. That has not changed. The only thing changes how many slabs we have. The slabs extend from 0 to 8 feet. That's why we're integrating from 0 to 8. And finally, the last variation of the same problem, part D. Yes, another question, certainly.
Why do you have another 1/4 inside that? Right.
Okay, remember that. Are you asking me why I didn't? Oh, excuse me. No, you're right. That 1/4 I should have gotten rid of. Thank you. Because if I factored my 4 outside, I don't want another 4 inside. Thank you. Okay. Okay, here's the last variation of the same problem. Call it part D. We're going to pump water out still, but this time it's going to go to a level 3 feet above the rim level. So it's going to go to a level of 3 feet above the rim. So this distance is going to be 3 feet. In other words, this is y equals what? Y equals 13. For this question, I'm going to give you a few moments, and then we'll come back and look at the answer. So we still want to pump it out, right, the entire contents. Once again, I'm going to pick a slab. Again, the thickness, the radius is x, the thickness is delta y. We've already done the groundwork. We already know the weight of the slab and everything. So we can use some of the past facts that we've gathered for this question. Instead of 10 minus y, was there a question? Yes. Or just stretching? Okay. Instead of 10 minus y, what should I have? So I'm copying the line from above, but instead of 10 minus y, I'm going to have, the suggestion I heard was 13 minus y. Would everybody agree? Because this slab has to be pumped to a level of y equals 13, right? So that means this slab has to go from here to here. It has to be pumped up to that level. And how can you represent it as a quantity, as a variable? Because we know from here to here is y. So this has to be 13 minus y, right? So that slab has to be pumped up to a level of y equals 13 from the ground level. So from whatever y level it is, it has to go further 13 minus y to reach that destination. So that's 13 minus y there. And how will we account for the fact that the container is full up to a level of 8 feet? How will that come into play? Integrate 0 to 8. Because basically the slabs physically exist from the point of 0 to the point of 8. So you're writing basically one delta W, one incremental work for each of the slabs, and then you're adding them up by the integration process. And anybody who did all that and got an answer for us? Because the container is only full up to a level of 8 feet. The water is only to the level of 8 feet, based on the given assumption. And did anybody get a number? Yes, 58,549. Thank you, Chris. Foot-pounds. Okay, I'm going to give you another problem to think about. Again, the first question was the easier one because you had a cylinder. In a cylinder, it's always the same radius. You didn't have to use similar triangle ratios. For a cone problem, the radius keeps changing. It gets wider as you go up. You have to use similar triangle ratios. Now I'm going to give you a spherical container, also one that doesn't have the same radius throughout the region. In a cone problem, we use similar triangles. In a sphere problem, we're going to use a slightly different technique. So here's the problem. I'm going to give you a little bit of time to work on this. Please remember, you got to pick a slab to begin with from your region.